Hello, welcome everyone to this video of OpenFoam. Now, as you can see, there is some data. Excuse me. Yeah, there is some data now of the heat exchanger. Okay, so this is our what case is this? This is the one with the constant density. We are able to I've run it for about 0.4 seconds in simulation time. And it's been running sort of overnight, so it's been running for a very long while. Yeah, so it's been running for a very long while, and here are the results. They may not be so physical, but at least they're stable. Okay, so let's go through them. So this is what the temperature profile looks like. It comes in hot. And then it's supposed to cool off a little bit inside the cold tubes, and then it's supposed to heat up here. Now that's what I intended anyway. But if you look at the boundary conditions I set, where are my boundary conditions? So okay, if you look at the boundary conditions I set for the hot side tubing, I give a Q value of 80 watts. I suspect that it's taking 80 watts out of the what do you call it? Out of the fluid, because this is supposed to be the hot side tubing, but as the fluid goes through, it's getting colder. So my guess is I need to just change the sign convention, and that should be fine. But this is a relatively small issue, okay, compared to what we were doing previously, okay. And the other thing also is that as the fluid goes through this bundle of tubes, we see that there's not nearly enough cooling here. There's just not enough cooling. All right. We have on the cold side tubing. Okay, there's a cold side tubing. So this is the cold side tubing. I gave it a H value of 20. So that means that, okay, it's supposed to be left in air to cool, stagnant air. Okay, so the heat transfer coefficient is not very good. So that therefore the cooling is not a lot. As you can see here, it's barely cooled 20 degrees. So there is insufficient cooling. But on the whole, there are results that show that the fluid is cooling through the tubes, and I'm pretty happy. So as you see here, as it goes through this right side, the so-called hot side, where I've actually by accident put in a cooling boundary condition, that has actually just started to cool down, and it's even cooled to sub 0 degrees C. Okay. But if you take a look at, on the whole, if you look at a slice plot, okay. Okay, hold on. Now, if you look at the slice plot, I'll unclick the show plane. Okay, I'll apply the slice plot first, and then I'll unclick the show. The show plane is off. If you look at the pressure, it's within reasonable bounds. The pressure drop is pretty reasonable. So nothing too much to worry there. Both P and PRGH are within reasonable bounds. It's not like 10 times atmospheric pressure at this point in time. So where do I see the pressure? You can see the range of the pressure is from 9.3 times 10 to the minus 4, all the way to 1.2 times 10 to the minus to the fourth power, all the way up to 1.2 times 10 to the fifth. And these are in pascals, right? Pascals. All right. All of these are in SI units. If we take a look at the temperature, okay, again, it's pretty stable, 500 Kelvin, and you see the whole left side is pretty hot now. And as it goes to the right hand side, it gets cooler. So we kind of need to increase the cooling over here and change this into a proper heating up boundary condition rather than a cooling down one. Okay, so I just probably have to change the sign convention to something like minus 80, for example, and that should about do it. Okay, so this is the heat exchanger results. On the whole, I'm pretty happy. Just need to change a few more boundary conditions. but the stability, it speaks volumes for itself. And this is a buoyant pimple foam. Normally it's not very stable, but we can see that as soon as we set this density to be a constant density, it becomes very stable. So that seems to be the trick to get it to work. Unfortunately, you remove natural convection, so you could think about adding it in using possibly by changing the density to be more of a quantity, more of a like a linearly varying quantity, and see what happens. I don't know. It might be stable, it might not be stable, but what we know for sure is that setting the density constant does make it stable. Alright, so next let's take a look at our CHD multi-region foam heat exchanger. Okay, CHD multi-region foam heat exchanger is over here. Okay, where is it? One pipe heat exchanger. Where do I store my stuff? Salome. Ah, yes, this one. Okay, so this is the shape of it. I'll just uncheck the internal mesh, and you can see that there is a reasonable result here. I'll just shift it to the latest time, and if you take a look at the temperature, it's a bit hard to see. Obviously you can see that the shell side is cold and that the tube side is hot, which is what I intended. Alright, so it's a little bit hard to see whether the hot side is cooling down or the cold side is heating up, because these two fluids are with very different temperature ranges. And of course this simulation is done with a coarse mesh, so it's not as physical as it should be, because it's not as physical as it should be because I didn't add the boundary layers, but it's numerically stable, doesn't go off the bounds, so that's the good thing. Okay, so let's take a look. Let's take a look at the shell side, for example. Okay, let's take a look at the shell side. So I'm checking off the tube internal mesh and copper internal mesh. Take a look at the shell side, and I will give it the T. Alright, so what we can see is that so shell side is supposed to be cold. So this is the inlet where it's let me see, inlet shell. Okay, so that's the inlet. Let me take out the shell internal mesh. Let me color it, maybe set block color as purple. So as purple, somewhere between red and blue. Oh well. Yes, purple. Purple is here. Yes. So I'll just set it as purple, and let me put back the internal mesh for the shell. Okay, where's the internal mesh? Shell internal mesh. There you go. Okay, so you can see that this is the inlet, and as the fluid goes through this medium, it gets heated up and it exits through the outlet. Obviously, there seems to be some hot spots over here at the end of the tube. That's normal because the fluid kind of gets stuck there, so it's not really doing much in terms of getting heat out. So this is okay-ish but not very good design in terms of efficiency, because due to this possibly due to fluid being stuck here towards the end, and it will be stagnant because there's no real reason to move around anywhere. But you can see that the shell side is heating up. Now, one thing to be very mindful about is when you can see that there are some blue portions over here, and these are actually at about 270 Kelvin. Now that's a bit concerning because 270 Kelvin is at 0 degrees C, and the tube side is supposed to be cold, okay, but not that cold. I put it at about 293 Kelvin, not 273 Kelvin. So this is actually for some reason the fluid temperatures over here are much colder, and that's probably due to numerical errors. Okay, so there are some numerical instabilities there which are causing this, perhaps due to the coarseness of the mesh, or something else, or maybe it's to do with the thermophysical properties. Yeah, but I won't go too much into that now. We can talk about optimizing this simulation a little bit later, but not in this video. Yeah. Okay, so the tube internal mesh is like so. We can rescale the temperature, and we can see that it works beautifully, because when the tube is this what do you call that? It is this it's in the hot side. It's a hot side, and then as it goes through the tube, it cools down, as it should be. So it goes all the way out over here, and that's the hot fluid getting cold and exchanging heat with the shell side. Okay, then of course the last part you might want to take a look at very quickly, but not too long. It's just the copper. The copper itself, it should not be very much. Okay, let me unset block colors. Unset block colors, yes. So you should not be too concerned here. Usually we have a uniform temperature, but since the copper tube is so long, we cannot assume that it has all of this constant temperature. In fact, there will be regions of the copper tube which are hotter than other regions, because the conductivity of copper, or rather the thermal diffusivity of copper, is not fast enough to get this whole part, what do you call that? This whole part, what? It's not thermal conductivity of this copper is not enough to get this whole temperature uniform. Otherwise, we can see that, let's see, surface with edges, yeah. Otherwise, we can see that it's pretty, at least it makes physical sense. So it's about 400 Kelvin, whereas the shell side is about 300-ish Kelvin. The tube side is about 500-ish Kelvin. So this is a reasonable temperature range. Of course, not completely physical. I mean, this simulation as a whole is not completely physical, but at least for the copper side, it is still reasonable in terms of temperature. Okay, so this is the shell and tube heat exchanger for you, at least the first stable iteration of it. Okay, so we could tweak this simulation a little bit more, but yeah, I guess that's all. And since I've shown you the results, I actually want to stop the simulation. Okay, I want to stop the simulation, and I'll just upload everything onto GitHub. Okay, so I'll stop this. That's the shell and tube side, and this is the salome heat exchanger side. And okay, PSA. Okay, so these are buoyant pimple foam simulation and CHD multiregion foam. The rest, I'm actually running something in the background, another buoyant boosted pimple foam case, but that you can just ignore. Okay, but now, as you can see, there is the experimental one pipe heat exchanger for salome. It actually works. I'll just make a few corrections before uploading. Okay, first I go to the 0 original file, I go to T. Let me VI system, CD system. Did I just delete my 0 directory? Oh no. Okay, hold on. Okay, let me try this. Since I'm in a git directory, let me git restore 0. Okay, git restore 0. Oh no. Okay, Oh yes, okay, this is the chdmultiregion multi-region foam directory. It's okay to delete the 0 file. Okay, let's see. Experimental one pipe heat exchanger salome. Okay, let me yes, all run 0 pre is here. Okay, so this is how you generate all the files. All run serial pre. Okay, so this will help you generate your 0 file again. So you just do that and chdmultiregion foam, and you should be able to run it. Okay, so I'll do it all clean. This this will be uploaded. Okay, like let's see, git status. All right. Okay, so I will just okay, I will just add this and git commit. Okay, what is this? chdmultiregion foam 1 pipe. Okay, let me try again. chdmultiregion git add and git commit git chdmultiregion foam 1 pipe heat exchanger stable but not physical. Okay. Okay, so that's one. The other one I want to kind of do is this part, the buoyant pimple foam heat exchanger. So let me just run an all clean here, and that will clear out most of the files. I'm not going to commit those to git. Okay, so let me just do a few minor adjustments, at least here. Let me change this to -80 so that maybe you'll have more of a insertion of heat, and then we can do this cold side tubing, increase the H value, the heat transfer coefficient there to 2000, so that the cooling is better. Okay, so that's should help it run 100 times, like it should help it run better. Okay, so let's go to system, decompose par, dictionary. So there's 6 regions. Okay, let me change the ORAN file as well. Okay, vi salome mesh gen. Okay, my time is up, but let me do the all run. Okay, so I will make it a parallel running case. Okay, let's see, salome mesh gen. Okay, that's what you run first. Then I put the run application decompose par override. Okay, and before that, let me see. Salome mesh gen. Oh, that comes with the all clean at the beginning, so that's fine. All run. So I do the salome mesh gen, which will clean everything up and restart everything. So run application not override. I think this should be force. Okay, then run parallel buoyant pimple foam, then run application reconstruct par force. Maybe I just do reconstruct par and let's see what happens. Okay, so let me try the all run script, all run n. So that should help run all of this in the background. So that's the poly dual mesh part. Just want to test the script out. It's going to do the decompose parallel. So it's going to have 5 of this, and it's going to run buoyant pimple foam. So you can actually tail. What you can do if you want to track what's going on in log buoyant pimple foam, you can do tail, and you give it the flag F, tail dash F log buoyant pimple foam, and you can see the results print out every now and then, and that should be good. It should be good. So let me kill this process 145642. So I'm just selecting this one. Any one of these will do, because that will stop the whole thing. Okay, and that should be all. Okay, I can do an all clean on this, and hopefully this thing is good. Git add dot and git commit with the message salome poly heat exchanger stable added. Okay, and I'm gonna git push it to GitHub, and these files will be available. Excuse me. Excuse me. These files will be available for you to use and experiment around with. Okay, so happy experimenting. Thanks for watching. I'll see you guys next time. Bye bye.